Okay, we're reaching the beginning of the end here. And, well, we decided to wrap up the conference with a panel discussion. And I think a bit of thought went into the panel discussion, and we kind of, going backwards and forwards, we decided to start focusing on correctness, so finding and spotting errors in languages. So, looking at errors, which you spot at compile time, at runtime, and beyond. So, before doing that, though, I mean, Sir Anthony Hoare, which we're very lucky and honored to have today, will, start with a quick overview over some of the constructs he's been working with. And from there, we'll then pass on to Bruce Tate, who will moderate the panel. So, yeah.
Well, thank you very much. It's really a great privilege and a pleasure to be talking to the CodeMesh conference again, especially since I've attended at least a day's worth of sessions and been very delighted at what I've heard, both from the keynote speakers and from the miscellaneous selections of London rooms. And I'm very grateful for this chance to address you at 5 o'clock on Friday afternoon. Thank you all for being here, but maybe it was partly due to the little bottles that I see in some of your hands. There'll be plenty of chance for that afterwards. And during, of course, I'm delighted to welcome the bottles too. One of the features of the keynote addresses, and indeed quite a lot of the more up-to-date presentations, was that they were quite keen on talking about history. And that, of course, is also very pleasing to me since, well, I'm already edging towards a bit of history myself. But I also want to talk about history. I'd like to talk to you about the very first programming language proposal that I put forward in 1964. It was, at the time, I was a member of the Algol working group of the IFIP organization, and we were engaged in developing the language Algol, developing and improving it over a period of some 8 years. And the first proposal that I put forward was called the case expressions, and we used to publish our proposals in a little mimeographed bulletin called the Algol Bulletin. And here I have copied out the first paragraph of my article because the ACM didn't allow me to give a screenshot. It is widely held that the switch mechanism of Algol 60, which was one of its less successful features, being both inelegant and inefficient in implementation. At the same time, there's general agreement. I don't know how I thought there was general agreement. I hadn't spoken to anybody about it before. But the conditional expression and the conditional statement, which only had just two alternatives, were among the most attractive features of the language, contributing greatly to the perspicuity of programs written in Algol as compared with, say, Fortran, which was the great rival of Algol in those days. The article continues with an example in which it gives a case expression where the numerical value of the expression to be discriminated on was followed by a list of alternatives, in this case 3 alternatives, of statements, the first of which will be executed if the number was 1, and the third if the number was 3. And of course, you've got a subscript overflow if the value of the case expression was outside the range 1 to 3. And this is implemented by a little jump table and an index jump in the same way as it is in many languages. In order to explain this to you more clearly, I've recoded this example in the C programming language, or what I was told at least was the C programming language, because I don't know C either. The example is written as a switch with the cases numbered also in a list. It's not a bad notation, a little bit cumbersome compared with the conditional notation. But there's a funny feature of this break at the end of every case statement, which is required in order to make sure that you don't accidentally start to execute code belonging to the next case. I think they put this in because they felt that moving on to the next case was, I don't think they could have thought it was a more common alternative, but at least if it did occur, it was more efficient to allow control to just pass through to the next case until you reached the break. So what happened, of course, as I think one might have foreseen, was that on one application of the language to a switching system, somebody forgot to do a break, fell through to the next case, and caused, I'm told, an outage in the telephone system in the eastern United States, which I would say was probably, well, at least a few $1 million of loss to the company and to its clients. And I feel that programming language designers should be willing to accept this as a reasonable criticism of the quality of their design. Well, at the time of this proposal, the alternative that people were discussing was to generalize a switch construct that was already in Algol 60, in which was organized as an array of labels declared as a switch. It's a constant array initialized to certain labels. And people thought that it was rather irregular. If you're going to have an array of labels, why can't we assign to them if we want to and make our own arrays of labels? And other languages have similar facilities of assigning labels to variables, assigned goto in Fortran. And in COBOL, they had something even more clever. It was called alter statement. If there was a jump or a goto statement already in the language, you could alter the destination of the goto statement so that on all future occasions that the jump is taken, it leads to a different place in your program. This was provided that the component number of your program was, I think, between 0 and 50, but if your program was numbered above 50, then it wouldn't happen because it would be stored on backing store at the time you wanted to change it. Well, I remember reading a very nice article in Datamation, which was entitled "The Come From Statement." Has anybody seen that? Oh, it was wonderful. It did point out that since what you're trying to do is to code in a linear textual form, what is much better expressed as a flowchart, then it's entirely a matter of choice whether you label the place that you want to come from and then write a come from statement in the place where you would otherwise have put a label. And they gave a number of examples and proposed this as an excellent. Well, the disadvantage, what the assignment of labels does to an array, and the jumping to an unknown label ensures at least a certain parity of confusion, that the label statement which receives the jump used to be able to at least look back and find all the places in the code that they could have been jumped from. And the come from statement, similarly, it enabled you to trace lexicographically the places that you might be going to. The assigned go-to, of course, gives you neither of these advantages. You don't know where you've come from or where you're going to. Well, sometimes I feel that way myself. Right, well, my next programming language design was published very shortly afterwards. It was called record handling, and it made a proposal that one should include into the next Algol language, something which is now known as object orientation. It begins, a method is proposed for the representation in a computer of a complex structured objects and for their manipulation by program. Furthermore, arbitrarily complex networks of relationships holding between the objects can be represented and manipulated by the program. I never used the word pointer because what I felt I was doing was modeling something which had an inherent meaning, that of a relationship between objects that we understand very well in real life. Of course, I knew, and perhaps everybody knew, that this would be represented by a pointer variable. Each record in the computer must belong to one of a limited number of disjoint record classes declared by the programmer in order to represent the relationships as well as properties. An entirely new type of value is introduced. It is called a reference, not a pointer, you may recall. It is natural to associate with a reference field or component of a record the name of the class to which all records referred to by it will belong. This is done on the occasion of the declaration of the reference field itself. Now, of course, this is a very familiar idea, but at the time that I proposed it, it was quite novel. Simulus 65, which had pointers, did not include any type checking. Simulus 67 did. The first language which adopted type checking of pointers, i.e. references, was one designed by Niklas Wirth, which was called Algol 65, or Algol W after Wirth. Here's my billion-dollar mistake, which you may have heard last time at a previous Code Mesh conference. In order to enable references to represent partial functions, functional relationships, a special reference value null is introduced. Well, of course, I have no reason to suppose it was $1 billion. I have occasionally consulted people who know more about the field than I do, and suggested the figure of $1 billion, and they come back and say something like What, you mean only a billion per year? Which is very consoling. And but most people at the last CodeMesh conference thought that I was accusing myself unnecessarily severely, and they wished to relieve me of the guilt of doing this terrible deed by pointing out that everybody did it anyway, or something like that. And here's a reference to the language description of the language, which included record classes, references, and garbage collection, of course, and those things I thoroughly approve of. I'll forget about those dangling regerences. I think I'll wait and see if there are any questions.
I think that we are very fortunate here. You guys can come on over. I think that we're very fortunate here at CodeMesh, and I came from Austin, Texas, and it doesn't feel like a long trip because this is such an excellent conference. I'd like to try something. How many of you in the audience, stand up if you have invented a language or been on a language core team? Just want to get a good, and you guys all count in the audience. So check out this density. Give these guys a round of applause. So we just have a small smattering of the language creators here. I've got to say I'm a little bit luckier. I'm here. The density up here is 80%. So, but I'd like to introduce to you Joe Armstrong, creator of Erlang, Josh Syme, creator. Don Syme, creator of F#, and Josh Watzman, creator of a language called Hack. And I'd like for them to each tell you the story of why they created their language. We'll keep this first question to about a minute.
Does this work? Well, I didn't know I was doing it. I think that was the best answer. It's a kind of after-the-hand. I mean, there wasn't a project to make a new programming language. We found ways of programming that became a programming language. And the main problem I was interested in was actually how to build fault-tolerant systems. So Erlang was not a goal in its own right. The goal was to make fault-tolerant systems. The problem that was being addressed was how do we make fault-tolerant systems, and Erlang was one of the answers to that problem. It's not a complete answer, but it's a partial answer to how you make fault-tolerant systems.
I started the F# language because I wanted the strongly typed functional programming paradigm as represented initially by OCaml, and also experienced it from other variations of ML and Haskell. I wanted that to be available to me in the context of .NET development and in the context of Microsoft development. Where I was at Microsoft Research, I wanted to make sure I had a language that I could use myself and be happy and programming in. And then it sort of went on from there. Yeah, but it was really, I think that's the best way, the best motivation for making any tool is to create something you want to use yourself, you and your peers.
Josh?
For Hack at Facebook, first I want to say that I was one of several people that contributed to the early forms of the language. I'm not in any means the sole inventor of it. Facebook realized that our web front end is written in PHP. It's very dynamically typed. You can have as much discipline as you want in a dynamically typed language, and that will certainly help you get a long way. But having a real type system, we thought, would help reduce the scope of a lot of bugs that we were finding, would help our developers write code more efficiently and be able to understand the code base via the type errors and via the code intelligence that you can get that comes with having a type system and the knowledge of your code base like that.
So you had a pretty large PHP user base. You had a project that maybe escaped from the lab a little bit and blew up. And you had a customer base that was really intensely dependent on PHP, and so this was the attempt to inject a little bit of type sanity to PHP.
Yeah, I mean, we had at the time, Facebook.com, tens of millions of lines of code with probably 500 million to 1 billion users, something like that. Everyone knows the scale of Facebook. And yeah, we can't, as much as we might like to have said, Mark Zuckerberg should have picked a different language, we're in a state where we can't rewrite all of that code, where our revenue is dependent on it, the people using Facebook are dependent on it. We can't stop development, we can't take down the site for 3 years while we use a different language.
I must say, Facebook is just extraordinary, both for funding that, but also to be in the position where you have 10 million lines of code and you can write a new language. You can afford to write a new language for it. It's really remarkable and wonderful to be in that position. Also that they did it in that situation.
And you mentioned actually injecting type safety as something, as a feature that you very much wanted to work with, and yet you were working in the early stages strictly with the CLR. So was that?
Yeah, that's right. The first major project I did at Microsoft Research was to inject generics into the design of the .NET Common Language Runtime, and actually that stemmed from an interesting project at the start of the .NET days called Project 7, which was about bringing many different languages to the .NET Common Language Runtime, and they engaged Microsoft Research early in that process, and I think that was allowed us to think, well, what are the foundations we need at the runtime layer to support an interesting and the programming paradigms that we want to see available broadly. Yeah. So
it's a type system is a very difficult problem. In IBM, we were trying to solve something with something called the system object model, with very much less success, I might say. But can you talk about some of the challenges of working with the types in the CLR that restrict what you wanted to do with F#?
Well, the key things that restricted us, which was the lack of efficient generics and the need to box far too much, we fixed through the process of adding generics to .NET. So I didn't really experience the CLR as a restriction. We fixed it to be what we needed it to be, I think. That said, there's the aim of the initial .NET design was to be a sufficient runtime system for a very broad class of languages. In reality, what we've seen is .NET in some sense narrow to be have one dominant language which is C#, a clone of that language which is called Visual Basic. It's effectively the same language in a different syntax and a different culture, and then F#, and then some other languages. But I think we have seen in many ways a narrowing of that field. There were, for instance, attempts to bring JavaScript onto the .NET into the multi-language ecosystem, and they didn't stick. JavaScript has all the JavaScript runtimes use other implementations. So which leaves open this big question, which is what is the common language? What is a common type system? What is a common API representation schemas and that we use to interoperate? And we see things like Swagger, for instance, for API description and to give some schema to the world of REST APIs, which is sort of overtaking as our common language. I still think it's this ongoing, recurring theme in language design is how do all these languages talk to each other and do that correctly without falling into this lowest common denominator trap. Where's that going to head over the next 5 or 10 years is a big question.
And Joe, I remember at CodeMesh, it was probably 3 years ago, you had a conversation with, I believe, Dr. Turner, Miranda. Yeah. And so I was just a fly on the wall listening and kind of, trying to pick my jaw up off the floor after, meeting some of my heroes. Yeah. And Dr. Turner looked at you and he said, I've spent my whole life working with type systems and strong types. I never would have thought that anyone would be able to create such a reliable system with dynamic typing.
I think you missed the start of the conversation because he said the first languages were with dynamic types. And I asked him, if he had a preference for one or the other. He said no, he'd work with it. They had their advantages and disadvantages. But my take on everything was slightly different. I was looking at entire systems. So to me, and to Robert Bearding and to Mike Williams, who worked with it, we were asking the question, what happens if the entire machine crashes? So I wasn't so concerned about the software inside one particular machine. I was worried about what happens for the entire system. And we intended to build this for the world's telecom systems. So we're talking about systems that are intrinsically distributed. And I just didn't believe, I didn't care if you've proved the program to be correct or anything like that, because I'm worried about the entire machine crashing, getting hit by lightning or something like that. So those are the sort of errors that no type system, type system's not going to stop you being hit by lightning. So I was addressing I'm looking at kind of architectural problems of how you build complete systems out of components that can fail. And then to me, dividing by zero was pretty much like being hit by lightning. So I was thinking I didn't want a different programming model for building very small systems and from building very big systems. So I didn't want the way you program to change and the way you reason about errors to change because you've changed the scale and you've changed the nature of the error. I was also thinking about systems which weren't started and stopped. I was thinking about systems that are in operation forever and which evolve. So the start point was completely different, and the goal was to build fault-tolerant things. And to me, I don't really mind if it's strongly typed or dynamically typed or anything. I think we need all these things to address different parts of the problem. And of course, if we can prove it to be correct, that's wonderful. But we can't prove it won't be hit by lightning. So.
I'd like to ask a question. So all of you were around in the very, very early stages of your languages. In what area did you pay specific attention to, I want to make this right before I want to make it fast or small or whatever you were going for? What particular features contribute to making this a platform for more correct programs? And we'll start with you, Josh.
Just the existence of a type system in PHP was kind of a bizarre idea at the time. But for the most part, for Facebook, we were actually tending to be on the side of the trade-off of we need our engineers to use this. So if it's 10% correct, but that's what we have to do in order to work, that's 10% better than we had before. I think we did significantly better than 10%, but we pretty consistently made trade-offs for performance, for compatibility, so that our engineers would be able to convert to it such that it was backwards compatible with PHP, such that we could maintain, since it was a project that was sort of off the side of the main compiler, one of our main constraints was we can't touch the compiler. The only thing we can do is add new syntax that the compiler drops on the floor. So there were a bunch of PHP-isms that we, I won't go into examples, but if you're familiar with PHP, there's a bunch of edge cases and stuff that we sort of tried to deal with in type system, and some of them required compiler changes, and so we just didn't. So we tended to make the trade-off for correctness when we could, but we wanted the performance and then the usability of it. That was the goal. We had to make it work for Facebook and for the engineering culture at Facebook.
And same question to you.
The initial aim, the initial core was very much guided by this core OCaml, core sort of camel-like programming model, the core strongly typed functional programming model, and doing that and Hindley-Milner type inference recursion, tuples, expressions, functions as values, pattern matching, and so on. And everything we did in F# has been, since then, it's been very important to us to preserve that core and your ability to just program away with correct code in that core you can always, everything else is kind of optional in a sense. It's additive, augmentative to that core experience. I think that so we're just enhancing that core strongly typed functional programming model with interoperability, with objects, with asynchronous programming, with with extra typing features, with type providers for F# and so on. Just keeping that core productivity in the zone. In the zone, I think. Yeah. That's why.
And Joe?
Absolutely. I mean, fault tolerance and having no errors in the system are absolutely central. I mean, the first two and most important things were the first one was fault tolerance. The second one was continuous operation, that if we did detect that there was an error in the system, that we should be able to carry on without stopping it. So we should just be able to continuously roll in new software. And that was because the products we wanted to replace had those behaviors. And we wanted to make something better than that. So it was absolutely central, and it was right in the beginning. And it led to this realization that, you know, if the entire machine can crash, you need 2 machines or 3 machines. And that led to the realization, well, they're going to operate concurrently and they're going to operate in parallel. So in order to do this, you have to start looking at distributed programming. So that was really very, very early, you know, that it had to be for writing distributed programs. And they were going to be concurrent, and that was the only way to do fault tolerance, because if the entire machine crashed, you have to take over another machine. So it's intrinsically distributed and concurrent. So it, you know. So I read your book and want to make something like that.
And Don, you've had the pleasure of working at Microsoft with just some fabulously gifted researchers and teachers. One of them is Simon Peyton Jones, and one of his favorite examples is of a side effect is that, you know, you can't unlaunch the missiles, right? So he always has a launch the missile. As you're aware, when you release a programming language, you are launching a missile, and there are some side effects, and there are some things that you've done that you can't take back. So I'm putting it on the spot a little bit, but are there some features that you wish you could take back?
Actually, I didn't have a prepared answer to that question. There are some corner case features that aren't worth the cost of the implementation complexity they introduced in retrospect. I mean, one would be structural comparison. So in allowing you to, when you define a record type or a tuple type, you can compare them for less than, greater than, and ordering. And that's just not worth it in terms of the complexity that introduces into the F# implementation. But we won't remove it now. I mean, it's done. That works. I did jot down some places where there are unsoundnesses, not so much in the F# language, but in the F# experience, which I kind of. So one thing I've learned over time is, for instance, that your package management, your library management software can easily introduce unsoundnesses into the experience of using your language. You know, if your package management and dependency management system doesn't tell you that you're not shipping a library that your application depends on, and you get you're relying on being a particular version being installed on a target machine, or isn't tracking version dependencies correctly, then it's an unsoundness, a big gaping, I think, unsoundness. Now, because we did F# in a particular context initially, which was, you know, .NET development initially, as it was 2003 or something, 2005, when we started, we picked up unsoundnesses from the ecosystem, of the tooling ecosystem around. And it's very frustrating to put a huge amount of effort into helping people write correct code on the system, and then find the ecosystem you're in is kind of a rotten empire where bad things happen because the tooling's not done right. Okay, now fortunately I think things like that they've certainly been fixed in the F# ecosystem. They're great package managers now and dependency managers. But it's more than the language. It's the whole process of software construction has to be sound. And we perhaps don't talk about that enough, those additional processes that are about delivering correct, reliable software.
Yes, we're seeing very much the same experience in a language I'm involved with, the Elixir language, and getting the package management right, and that means getting dependency resolution right, and where are the right places to have exceptions, and there are a lot of places to make a mistake. I need to go home to Eric and tell him it's okay. It won't be a $1 billion mistake, right? So you gotta,
right.
And the same question to you, Josh.
So there's nothing that I would say, like, unequivocally, we shouldn't have done that and take that back. There's a bunch of places where we did things for backwards compatibility with PHP where the type system is gradually typed, meaning the programmer can explicitly omit types and have holes in the type system. And that's fine, and you can have a switch that says, like, no, seriously, there need to be types everywhere, this needs to be sound. But other than those, there's a bunch of corner cases where the type system has holes that you wouldn't necessarily expect, that makes sense if you're trying to convert existing PHP code. But I wish that we had done a more thorough evaluation of what all of those places were before we open sourced the project. One of the ones I can think of right now is that if you're using a PHP array structure and it's heterogeneous in certain ways, then the type checker just gives up. And it doesn't say anything, it just gives up. And that made sense at the time, but we're now, like, it doesn't anymore. We're having to unwind that, and it's much more difficult when your project is open source and there are people using it. So I wouldn't say that I wish we could take that back, but I wish we would have thought whether we should have done that beforehand, because I'm not sure if that was the right decision.
So there are trade-offs, right?
Yeah.
And sometimes decisions, so every decision is a compromise, and sometimes conditions change. And
Yeah, exactly. And like the project had been in use at Facebook for, in some form, for a year to a year and a half, quite a while. And so a lot of the decisions that were made in the early stages of the project were the right decision then, aren't necessarily the right decision for Facebook when we released it and for the people we were releasing it to. And we should have thought some of those things through again, and we didn't.
Sure. And Joe, so you've got one of the toughest positions on the stage because Erlang's been around a long, long time, right?
Yeah.
And there's a lot to second guess.
Yes.
But what are some places where you might have made a compromise that you might make differently this time?
Loads of places. To start with, a lot of the implementation was dictated by the pragmatics of the machines at the time. They had a small amount of memory. It had about 8 megabytes of memory. And systems then weren't intrinsically distributed. I mean, the notion of two computers being easily able to talk to each other was impossible. So from the mid-90s onwards, communications become ubiquitous. We've got 100 megabit links between computers. So distributed programming suddenly appeared as a ubiquitous thing. And that wasn't the case when we did Erlang. We didn't have much memory. So we would do things very differently now if it was being redesigned. And then in the language, I think there are, I would like protocols to be first-class objects in the language. We could reason about protocols. So the protocol is now, today it's something that's on a sheet of paper outside the language. It's not bolted into the language. And it's the programmer who makes the connection. There isn't a formal connection between the protocol and the implementation. And I would like much more formal checking of contracts on boundaries and things, because nowadays we connect large numbers of things together in chains, and if any of them fail, it's very important that we know. I'd like to make things of very small components that talk to each other and do well-defined jobs, and if they fail, we know that thing has failed. We tend to make very big components, and they tend to pass their errors on to somebody else, and we don't know where they failed. So I would like to see architectural changes. And I'd like to make the number of objects we could address much larger. I mean, we're talking about processes. An Erlang node can have maybe 4 or 5 million processes. I would like it to address all the processes in every computer on the world. I'd like it to address trillions of processes. I mean, things like email and things should be as simple as just sending a message to a named process. And the system should just handle it, because then a lot of problems will just vanish.
So at this point, I'd like to ask an open question to the panel. Is there something that you see in another language that you think really contributes to correctness, that you wish that you'd done in your language, or that you really respect? And Tony, you could answer this one as well if you'd like.
Oh, can I choose after everybody else's?
Certainly, yeah.
Yeah, I'm thinking. I'm sure there are. I'm just thinking.
So let me go ahead and get this one started. There's a when I worked on 7 more languages in 7 weeks, and by the way, after writing that book, I really wish that I picked F#. I became a big convert after going to a conference in Norway. Really love that language. But we picked a language called Idris, which did dependent typing, and I thought, as I was coding in this language, I thought this is really changing the way that I think about productivity and correctness, and it really it sharpened the focus of the tooling. It sharpened the focus of working with the model, and really helped me think about why null was a bad thing. So I really enjoyed my experience in Idris.
Yeah, it's a difficult question to answer because as a language designer, I guess you become very sensitive to the fact that adding a new feature to the language pushes some programmers out, okay? Some people can't use it anymore because they can't learn that feature. It changes the way the language is used in talking and communicating of code, may make code more inaccessible, less accessible to certain programmers. So you're aware that everything's a trade-off, everything's a distortion. So you can't just say, I'd like that, because you go, oh yeah, but if I added that, then, something else, you're distorting the whole equilibrium of where the language is at. And it's not all about features, what we focus on F# at the moment enormously is cross-platform and open source, and making that a reality for the language. And that's something you see in other languages, and we've worked very, very hard over the last three years to make that real for F#. So I guess that's the sort of thing where when we grew up in the Windows ecosystem, where we looked across and we thought, yeah, okay, we got to do this, we got to do it well, and focus on that. And so I guess that's where I feel it's also about scalable data systems, Spark in Scala, wonderful system, yeah? And we want some of that, and so we're doing that, we're doing the work to make that real in the F# ecosystem, but so I don't feel the jealousy of the transferring language features by jealousy, it is the best way to do tech transfer. At Microsoft Research, the best way to have influence on a product team is to make them jealous of some feature. It's been great with C#, it's been awesome. Yeah, you just load the demos and they see that, oh, that F#, I want that, yeah.
So you said one thing, you said community, and I think that one very important thing to consider to making programs right is having the right programs on the project. And one of the things that you've done very effectively is moved F# beyond the stewardship of Microsoft, so that you've really expanded that community. Could you talk a little bit about what that process was like and the impact that you've had on the language that way?
Yeah, I put out a blog post recently which was saying, look, when you use the word F#, please, when you're referring to what Microsoft do with F#, please use the product terms, Visual F# or the F# tools for Visual Studio. Microsoft contribute a huge amount to F#, but we've liberated it to be in a sense a broader initiative. There's lots and lots of community-driven stuff. There's lots of cross-platform stuff. There's lots of open source working. People are taking F# in all sorts of places, and so the word F# now should be like every single good industry language. Should be considered a free term, in the same sense a closure is a free term, or Scala is a sort of free term. Free in the sense of not having such strong mental associations with Microsoft or Visual Studio or whatever. And that's the right thing, because it's actually the right thing for Microsoft, because we're becoming, if you look at our product directions with Azure and the cloud platform, we're open to all sorts of things. It says, hey, you do Go, come and do it on Azure. You do Linux, do it on Azure. You do everything. Come and, we're a much more open kind of company than we were before. So it's right for Microsoft. It's definitely right for F#. It's right for the F# ecosystem. And now the process of getting there has been a strange one, because I actually always, being a researcher, I always wanted to head in that direction. And then suddenly, the whole of Microsoft came following, right? We were making sure that F# had a great cross-platform existence, and then Microsoft came following in a herd to also do very similar things with C# and a lot of our tooling so that we unexpectedly led Microsoft, but we didn't. I mean, they went there because of this sort of cloud dynamic in the industry. The whole cloud thing cloud and devices thing moves towards much more open technologies. Open source itself is an incredibly strong economic dynamic. And it's just great that our shift in that direction for F# and the community also corresponded to the whole world going in that way.
So does anybody else want to take a shot at that question? And the question is, are there things that you've seen in other languages that you respect, and maybe you want to implement it and maybe you don't, but that really contribute to correctness?
So not necessarily correctness, but in general, like things that I wish we had launched with. What you were talking about tooling, like our installation process on day one was terrible. We didn't really have any tooling around the language. The bits we had at Facebook, we hadn't gotten to open source yet. So as far as like bringing the correctness to other people, like I can't overstate how important it is to think about the tooling and then the general ecosystem around your language. The language features that you have, the shiny correctness things, is secondary if nobody's using it.
Yeah, I think things like John and Mary talk about quick check and quick checking hardware look very promising, and I'd be very interested in reproducible builds and being able to describe the state of systems accurately. Because I mean, at the moment you don't know what state the operating system's in, and so if you report an error, say, well, I did this on my computer and it crashed, and somebody else says, well, do this, and it doesn't behave the same way. So, I mean, if we had things like a Smalltalk image and you had the SHA1 check some of it, and you said, well, we started in the same state, at least you'd have some chance of finding where errors were. So I think things like reproducibility of builds in systems, I don't really like them being outside the, I don't like things being in Git and being sort of distinct from the language. I'd like to see much more integration with the languages. So, I'd like to refer to modules by their SHA1 checksum or something like that, so I know exactly what it was. There's a sort of spectrum of precision in naming things. Basically, I like to do away with names totally because they're transient and their content can change.
And Tony, do you want to take a shot at this one?
You offered me before, I said I would. All right? Do you want me to?
There's another time for another
question. Right. Since I'm not a designer of a programming language and never have been, I haven't really had the opportunity to look jealously at other languages. One thing that has really impressed me recently is the separation logic concepts that were introduced by Peter O'Hearn in his concurrent separation logic language, which seemed to be a potential solution to the problem of race conditions in a shared memory computer system. So I would look forward to that being recognized and implemented in tools as a means of solving a problem that is probably of the order of $1 billion quite easily. I would like to also support the view that it's the tools where the action is, not the languages. The compiler is only one among a whole battery of tools that are now essential to work successfully together in the development, design, specification, coding, testing, delivery, certification, analysis of all the programs that we use today, and in particular, I would like to have concentrated more on the evolution of programs after first delivery. When I was an academic, my model was that you sat down with a piece of paper and you wrote a program from scratch. And it wasn't until still in Oxford we started teaching professional programmers from IBM in Hursley that we discovered that none of them had ever in their career started off to design a new program. It was all maintenance. And I think that's even more so today. So as a theoretician, what can I do to help in the development of these integrated development systems? Well, I think my contribution I would like to be to see the need for a unifying theory on which all the tools can be based. A theory that would apply to many different languages, and a theory which could be specialized to the needs of the individual tools which are applied to those languages. So more languages, yes, certainly, but they all need tooling. Are they all going to have their own separate tool sets? No, they are not. Therefore, we must make our tools not only agree with each other, but also make them adaptable to the needs of many different programming languages. So this is overall a project about equivalent to the original ideas of a compiler, which would enable you to generate compilers automatically, is much more adventurous and ambitious than that. And that, of course, is something that has never happened anyway. So I hope there will be good news in the future. At the moment, we have a problem of tooling for a multiple language system.
That's a great way to wrap up. Let me point out that that there are people that aren't on the stage, with Elm and Julia and Haskell and Pony and Scala, and I'm sure that I've left a bunch of them out. But thank you for all your contributions to the conference. Thank you so much to the language creators and early contributors that are on the stage. And I'd like to invite Francesco up to wrap up the conference.